sampling rate conversion. Okay. So we should talk about three cases. One is called, the first one upsampling, the second one downsampling. The third scenario is that if we want to convert the sampling rate by some kind of ratio, 5/3, 2/7, or something, anything like that. So we have the issue of upsampling, of downsampling. And resampling. That means to convert the sampling rate by any ratio. Okay? So when we say upsampling and downsampling, that usually means the sampling rate, the ratio of the sampling frequency before and after conversion. That ratio is an integer. Up by an integer factor, down by an integer factor. That's called up and down sampling. But if we want to convert the sampling rate in any ratio, any arbitrary ratio, then that's an issue of resampling. Okay? And for those of you that are familiar with MATLAB, MATLAB actually provides a function that's just called resample. And you specify your signal and the rate before and after sampling. These are well-established things that you can simply use for MATLAB. But now we're going to talk about the general principle, how that works. Okay? So for upsampling, the meaning is that, so let's talk about upsampling. The idea is that if we have, you're given a discrete time signal, that is a sequence of numbers. So suppose that this is your, I'm not going, I need to take care of the spacing. So let's say we are given a discrete time signal, X of n. And somehow we want to expand it so the sampling rate becomes twice as much. Okay? So suppose that our task is to increase the sampling rate by a factor of 2. By a factor of 2. Okay, so that means that for somehow we need to insert points in between. We need to be inserting more points in between samples. That's the meaning. Okay? So what should happen in half integer places? If this is n equals to 1, 2, 3, and 4, right? So to upsample by 2, we need to figure out what values we should put in between samples. Right here, right here, right here. In between samples, we need to insert more points. So how do we do that? How do we do that? And the answer is still, let's consider interpolation. So this is a matter of interpolation, right? You want to figure out how to insert the value. Whenever you do that, that's interpolation. Okay? And so the suggestion is that you should probably put a sinc function. So consider that for better or for worse, we are going to just reconstruct the analog signal first, and then resample at 2 times the original sampling rate. Okay? Suppose that, so the suggestion is going to be, it's going to have 2 steps. Okay? If you want to come to upsample by 2, then the suggestion is, at least conceptually, the suggestion is first, let's just do D2C. Let's just do D2C to reconstruct the original, to reconstruct the signal in continuous time. And then simply once we get a version, a continuous time signal, we can always resample it at any rate we want, right? So now we can resample it at what? At 2 times faster. So let's set the sampling period here to be half as our original sampling period. That means the sampling rate is going to be 2 times. Okay? So conceptually, this can be done. Okay? And let's call the result of being x, I, and n. I stands for interpolation. Okay, so that's a kind of suggestion. 2 steps. First step is, let's just perform D2C. Second step, resample at twice faster. 2 times faster. Easy enough, right? That should do the job, okay? That should do the job. So that should do the job. But it's kind of hassle to, that means that you need to have your sound card ready. That means that you put it in kind of in practice. Of course, this can be done, but somehow, in order to do that, you need to go through the hassle. There's a lot of work to go through D2C conversion. So, in reality, let's say you have a file, a digital file, audio file, for example. Then this is to say, I'm suggesting you to use your sound card. First, play the signal, and then re-record using your computer. That's kind of, can we avoid going back to the analog thing? That's the question. Can we simplify it? Okay, can we simplify it? Okay, so to come to think about this, we are going to suggest that in reality, to avoid coming back to the continuous world, continuous time, to the analog world, to avoid that, we are going to suggest 2 steps. And this is going to be completely in the discrete time, in the digital domain. Okay? So the suggestion is, still we have x of n as our input. And let's first expand the signal. This is called expansion. Okay, I'm going to define it in a moment. Let's expand it, and the result is denoted as x sub e of n. E stands for expansion. Expansion, 扩张开来。And this can be done. We'll show in a moment. This is a very, very easy process. And then here, after expansion, now we are going to suppose that the sampling rate has been changed. Okay? And then what we do is a low-pass filter. Low-pass filter with a cutoff frequency. With a cutoff frequency at pi over 2. And the result, xi of n, should be exactly equivalent to what you would get in an ideal D2C, C2D conversion. Okay? So that's our suggestion, our actual suggestion. To upsample, taking the example of upsampling by 2 as our example. We will first expand the signal and then perform low pass filter. Okay? And so that's our idea. Okay, so that's pretty much what I want to share with you today. But let me just finish by also telling you to perform downsampling. It's quite similar, but perform downsampling, we want to perform low-pass filter first. And taking downsampling by a factor of 2 as the example, we want to perform low-pass filter first, and with a cutoff frequency also at pi over 2, and then perform a decimation, and then perform this down by 2 operation. Okay, but down by 2, so that's kind of, we will talk about this sort of reasoning, the difference between upsampling and downsampling. Next time we meet, that is Thursday at noon. Okay? Thursday we'll be meeting at noon to make up for my absence. Okay? So that's all I want to say for today. Thanks for coming and see you on Thursday. So that's kind of some remarks for the example we discussed 2 days ago. And today, let's look at, first let's look at upsampling. Okay, so suppose that we have some kind of a discrete time signal with sampling period of t. And suppose for some reason we want to increase the sampling rate by a factor of 2. We increase the sampling rate by a factor of 2. That means that we want to insert points in between our existing samples. We want to insert some values. We want to do an interpolation. So I mentioned that conceptually, to change the sampling rate in general, so not necessarily in upsampling, but also downsampling for any given arbitrary rate of conversion. In order to change the sampling rate, conceptually you can think of applying D2C first. Let's get back to the continuous time domain first, and then resample. So that's an idea, right? So at least if we follow this idea, let's conduct a D2CC conversion, which is the best way is to apply the ideal low-pass filter, who has such and such cutoff frequency. Okay, so we've been suggesting that to a D2C, ideally you want to apply sinc interpolation because ideal low-pass filter in the frequency domain would be equivalent to sinc interpolation in the time domain. Okay, so let's do this sinc interpolation. So I'm kind of drawing a cartoon, a picture here. Sinc interpolation. We can always do that. Okay? Conceptually, it can be done, right? And then the next thing is to resample. Okay, the next thing is to resample. So the next thing is to resample. So now we know in this sample, okay, let me use another color. So after smoothing maybe the signal loop, now look, after sinc interpolation, after superposing all the copies of sinc functions, the shifted copy of sinc functions, then we have this, let's say we have this yellow curve after D2C. And then simply we'll be able to resample at half integer values, at half integer times. So fair enough, okay? Conceptually we can do that. But I was suggesting, like in the final minutes, I was suggesting that, in fact, this only needs to happen in your concept. I mean, we don't need we do not actually need a D2C converter to achieve the job, to achieve this goal. The entire interpolation can be done in the discrete time domain. Okay? So here's how we do that. Or equivalently. The equivalently, we are going to suggest this expansion operation. First, suppose that the input is x of n. And we will expand it, and let's denote the result as x sub e of n. where E stands for expansion. 把它扩张开来 expansion. And then after that, we will apply a low-pass filter in the discrete time domain. And we will need to determine the cutoff frequency over there. Okay. Let me tell you the cutoff frequency actually is the cutoff. C stands for cutoff. In this example of upsampling by 2, the cutoff frequency will be pi divided by 2, so we can easily generalize. If we ever want to upsample by 3, then yeah, expanding by 3, but then followed by the low-pass filter with cutoff frequency pi divided by 3. Okay? So these two and these two are actually the same thing. Right? So that's our suggestion. The result is whatever. The result, let's call it YFN. Okay? The result is an upsampled version, will be an upsampled version of S of n. Okay? So this is what we suggest to do in the time domain. So let me specify what is expansion exactly. What does this block, does this symbol mean? So here, x of E of n is fairly simple. It depends on n is even or odd. Okay? So x e to n will be defined as x of n divided by 2 if n is even. Oh, sure, even number. Otherwise, it's 0. Okay? Simple enough. So basically, if x of n is here, 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 this is where we originally have values. If this is x of n, I use phi to represent the index n. Okay, x of n be 1, 2, 3, 4, and 0. Okay. So to expand it, let me use another color. So to expand it, let's change the time index 1 to 2, 2 to 4, 3 to 6, and 4 to 8, and so on and so forth. Okay? Then, exactly the same type tells you what is the x expanded version, the xe of n. Xe of n, let's say n prime. Okay, n prime actually is 2, 4, 6, 8, double the n. You know, it's double the n. Okay? And then after expansion, we say that for odd numbers of n prime, which is 1, 2, 3, 4, 5, 6, 7. Okay, the odd numbers, we just temporarily set it to 0. Okay, so the result of expansion will give you something like a sample and 0, and another sample and 0, and another sample and 0. So that's just simply a definition. So in this way, we have expanded the duration of the total number of samples after this operation. Okay, that's simple enough. Can we continue? Okay, so that's very simple. And then applying, so the next step, so this is upsampling by 2. How about low-pass filter with a cutoff frequency at pi over 2? What does that mean? To cut off at pi over 2, let's come to the frequency domain. Suppose that we have an ideal response, which is 1 within the passband from 0 to pi over 2, and beyond that is 0. Okay, so that's the meaning of low-pass filtering with a cutoff at pi over 2. Okay? So if we calculate the inverse Fourier transform, we know that the inverse transform of any this kind of low-pass filter is a sinc function. And since the cutoff frequency is exactly the Nyquist frequency divided by 2, we know that the narrower in the frequency domain, the wider in the time domain, right? So we expect to see the inverse transform to be a sinc function, but which has 0 crossings at even numbers, at n equals to 2, 4, 6, and 8, and so on. What does that mean? So I mean, we expect the inverse transform to be something, it's still a distinct function, but zero crossings are spaced, but it crosses 0 at even number, at n equals to even number, okay? Even integers. Alright, so if we accept that this is the inverse transform of our ideal low-pass filter with this cutoff frequency, then let's try to convolve the green the XEFN with, actually I shouldn't draw a continuous time. I should emphasize, no, it only has values because we are in a discrete time here, okay? So this is the convolution, the thing that we are going to convolve with our green signal. Okay? The signal is the color green. Okay? So if we convolve the green with the yellow, then whenever we see a spike, we put a copy of the sigma function, right? And so on. And so we are going to sum up. So I hope you have seen that equivalently we are doing sinc interpolation, not everywhere, but only at odd number places. So that's the kind of beauty, the simplicity of doing everything in the discrete time domain. So I want to show you that just by completely do this, know that there are two steps here. Let me finish drawing the picture, okay? So equivalently, now we are doing this sinc interpolation completely in the discrete time domain. Okay, that means that we are going to calculate the interpolation only at time, only at t equals to n equals to 1, 3, 5, 6, 7, and so on. Okay? So the result will be something like this. The result, you can just draw your own picture. Okay? The result is something like this. And so on and so forth. So one way or another, the mathematically, you can convince yourself that these are equivalent. But the beauty of doing this is that we do our the minimum requirement, so to speak. Okay, since we only need to upsample by 2, so all we care about is how to insert values, right? So to do the interpolation, we don't need to interpolate like that everywhere. We just need to calculate the interpolation at, again, we just need to insert one point in between every pair of adjacent points. Okay? So this is what we are suggesting to do to perform upsampling. Okay? Well, this is kind of an explanation in the time domain. So let's complete our picture in the frequency domain to see what happens when we perform expansion. Okay? Expansion in time domain. What happens in the frequency domain? That's the question to ask. Okay? So let's study what has happened in the frequency domain for this chain of 2 actions. The chain of 2 actions. The first action is to expand the signal. So to expand the signal, the question is, what happens in the frequency domain? In the omega, okay, in the frequency domain. What happens in the frequency domain? Okay, we can always do a straight mathematical derivation. Okay, so what happens in the frequency domain? That means that I want to calculate the Fourier transform, the discrete time Fourier transform of this signal. Okay, the discrete Fourier time, the DTFT of this signal. So the DTFT of this signal is denoted by big X sub e to the j omega. By definition, should be equal to the sum of all possible n, and let n run from -infinity to infinity, and then we put x E of n here with e to the minus j omega n, right? That's simply the definition of DTFT. But then, we know that xe of n, the green thing here, has non-zero values only at even numbers. Right? Only at even numbers. For all the odd numbers, it's still zero. It's still zero, right? So this we can change the summation index. We can change the summation index to should I say summation? What is the best way of saying this? Okay, let me actually put numbers in here. It's easier this way. Fe of 0 and e to the minus j omega 0 plus xe of 2 e to the minus j omega to the exponent 2 over there, and so on and so forth. Okay? But what is xe of 2? It's just the original signal taken, measured at time 1, right? So this thing here is actually x of 1, the original signal. So, but now with x of 1, we have an exponent, a 2 showing on the exponent. So I'm trying to convince you that, therefore, by observation or by a change of variable, we can see that xe, the spectrum xe, the spectrum after expansion in time domain will be exactly equal to the original spectrum, but evaluated at j times e to the j2 omega. If it's not clear yet, let me put one more term here. So you can do that by yourself too. xe of 4 e to the minus j omega 4. Then this signal here is, this sample here is equal to x of 2. Okay? So a summation of x of 0 e to the minus j omega 0. So it's 1 here, 2 here, 2 here, 4 here. So that's why we have this relation. Okay? Expansion in the time domain corresponds to compression in the frequency domain. If we stretch in one domain, we squeeze in the other domain. 伸长跟压缩的意思。Because the expansion in time domain makes the signal look longer. Right? In the frequency domain, we have this equivalent relationship. Oh, I hope this is clear enough. Is it clear? Is it not clear? Okay, because by definition, this will be the DTFT of the after expansion, right? And just by change, essentially this is a change of a change of variable, a change of time index. Okay, so we realize that this summation, this infinite relation, turns out to be exactly the DTFT of the original signal, but evaluated at double the frequency. All right. So if this is acceptable, then we can draw what's happening in the frequency domain. Okay. We know that. Suppose that we have the original spectrum that looks like band limited real behavior. And we know that all the DTFT is going to be periodic with respect to every 2 pi. Okay, so for at minus 2 pi, I have the same thing. The spectrum is always periodic. And this is the original spectrum. And then, what is the original spectrum evaluated at double the frequency? How do we draw that? How do you make a picture out of that? And the result is very simple. It's simply what I said. Expansion in the time domain, compression in the frequency domain. Okay? So we are going to see like sigma triangles. So now this spectrum is going to be periodic, not every 2 pi, but every pi, because the frequency axis has been compressed. So let's draw it carefully. So now everything looks narrower because of they should be equal height. Okay, so you don't know that. So it's going to be becoming periodic. The period in the frequency domain becomes smaller, becomes half, becomes pi. So it was 2 pi there, but now the period becomes pi in the frequency domain. And this is our spectrum of X after expansion, because it simply is the original spectrum evaluated at double the frequency. Okay, so that's the idea. That's the way to draw a picture out of this. So this is after expansion. Okay, so that is to say, now the Fourier transform of this green thing here, the green signal, which is something then 0, something then 0, something then 0, something then 0. The spectrum of this signal that kind of alternates, fluctuates a lot, has one triangular shaped spectrum component, a chunk here, but also it repeating itself every pi. Now what is pi? Pi is the Nyquist frequency. So that means that this signal has some kind of spectral component near the Nyquist frequency. It's oscillating very fast. And that agreed with our observation in time domain, right? Because it's something 0, then something and 0, then something and 0. So that's why we have this unwanted pi that we want to get rid of. And that's why we suggest we need to low-pass filter with a color frequency at pi over 2. Okay, so this explains why. It shows us why, the reason, this motivates us why we want to apply a low-pass filter with the color frequency right here at pi over 2. Because everything here, because this chunk of thing is unwanted, we want to remove it. Okay, so that's why we apply it after. So we suggest you would apply a low-pass filter. Actually, this is kind of stupid. I don't even need to draw this part because it's going to be periodic. Okay? It's going to be periodic. But the important thing is that we want to remove this highly fluctuated component. We want to get rid of that because it corresponds to nothing here. Because this thing really corresponds to nothing here. The original spectrum has only from 0 to pi. Okay? From 0 to pi has a very nicely shaped triangle, but here we have one extra thing. We have some extra thing going on near the Nyquist frequency. And then it is unwanted. So this explains. I just want to share with you. This is the way we look at the entire chain of actions. 2 steps: expansion by 2, then low-pass filtering with a color frequency at pi over 2, and it's probably clearer to see into the frequency domain. But in the time domain frequency domain, things are equivalent. Okay? So thus, we have this suggestion. If you ever want to upsample by 2, this is the procedure, 2 steps. Okay? If you want to upsample by 3, just you can generalize. By 4, by 5. It's all very similar. Okay. Any questions so far? Any questions so far? Okay, so our next topic naturally is downsampling. Okay, and the suggestion is to first perform low-pass filters. And still we are going to oh yeah, yes. Okay, let's change gears. Now we are going to perform downsampling. Okay, and let's take the example of downsampling by 2. So in one or another, this means that we need to kind of the simplest idea, which is problematic. Okay? The simplest idea is that okay, if we want to downsample by 2, that means that we need to pick and choose. We need to sort of remove half of all the samples, right? Downsampling by 2. Think of imaging. Like you always, like this is pretty clear. We all have cell phones, right? In 2D signal, that is digital images. Sometimes we zoom in, sometimes we zoom out, right? We tend to change the size of the image, right? And so when we enlarge the image, that means we are upsampling. When we downsize the image, that means we are downsampling, right? So we know that the total number of pixels will change. So in the scenario of downsampling, the total number now going to get back to time domain. The total number of samples will become 50%. So we need to somehow get rid of half of all the samples. Okay? But so that action here to delete every other sample. This means to delete every other sample. Okay? But we suggest that the suggestion here is that we need to perform low-pass filter first. And again, at the cutoff frequency of pi over 2. And then only after that, we can just freely remove, just pick every other sample and drop all the and we can pick every other sample and drop half of them. Okay? So that's downsampling by 2. Okay, so let's call the signal here, let me have a notation. Or what do you want to call it? How do you want to call it? X tilde. Okay. Let's call the signal here X tilde. And the signal here X D tilde. Okay? Where D stands, again, it stands for a word. D stands for destination. So the definition is Xd of n will be simply x of 2n. So we are skipping all the odd number samples, right? We are saving all the even number samples while dropping all the odd number samples. That's the meaning. Okay, so this part is easier. Okay? This part, what we mean by this destination is that we simply drop every other sample. So if x tilde is 0, 1, 2, 3, 4, n, 1, 2, 3, 4, then x then after destination, the time index changed to become, now we equivalently have a lower sample rate, that's the meaning. Okay, we are dropping every other point. We're dropping every other point here. Okay? So, but if we look at, again, ask the same question, what would happen in the frequency domain? Let's ask the same question. What would happen in the frequency domain? What happens in the frequency domain for destination is that now, by definition, the spectrum after destination will be, whenever you pick and choose, the lower the sampling rate, you can expect aliasing here. You can expect aliasing here for exactly the same reason, for same sort of mathematical notation. Okay? This is the highlight. I'm not going to go through all the mathematical details. But here, xd of any time domain, when we drop every other point, it is equivalent to first, equivalently we are first multiplying our signal with the SHA function, with the sequence of spikes. So recall this is very similar when we talk about sampling the signal. Okay, so the idea is that when we are dropping every other point, equivalently we are first multiplying our signal with this function. Let me call it S of n. Okay. We are multiplying our signal with S of n and then perform kind of a change of rate. I mean, just replace n with 2n. Okay. So now we can. So now asking the question, what would happen in the frequency domain? What will happen in the frequency domain when we multiply our signal with this kind of selection function? Okay? Let's not for now call it a selection function. We are selecting points and ignoring points. Okay? When we multiply two signals in the time domain, what would happen in the frequency domain is convolution in the frequency domain. Okay? So if the original spectrum look like, it is periodic for sure because we are already in discrete time. But if this is our spectrum, and we are going to multiply it with this selection function. Now we know that the selection function is basically, we will have extra copy in here. We have extra copy in here. Because why? Because the Fourier transform of this selection function are also a sequence of delta functions in the frequency domain with the spacing. So here, the time domain spacing is 2, but here the frequency domain spacing is I. All right, okay? So, that means generally we should worry about aliasing. Okay? Suppose that if your original signal, does everybody see this? Whenever this also happens in the image domain. Okay? When you downsample the image, like, we should look at some examples. Like, in image, okay? If the original image has like high frequency component, like densely spaced stripes, 有些条纹如果有接近的条纹 densely spaced stripes, that means in 2D it has a high frequency component. And have you ever noticed that if you just downsize the image by 2 in x and y direction, sometimes it could happen that the stripe becomes low frequency. Have you ever noticed that? After downsizing, sometimes you see like patterns that does not exist before. Does anybody know what I'm talking about? Okay, so this is an example of 2D aliasing when you downsize the image. And here we talk about the same thing. In the time domain, when we simply remove every other point, effectively what we have done is to multiply our signal with the selection function. But the selection function has a frequency, has Fourier transform which consists of spikes, Dirac delta spikes spaced by pi, every pi. So when we multiply in time domain, we convolve in the frequency domain. That means that we are placing extra copies of our spectrum at pi. So this example of downsampling by 2. Okay? So placing one extra copy of our original spectrum at frequency near the Nyquist frequency. Okay? So now, in general, we would expect aliasing, unless unless we are so lucky that the original spectrum does not have any frequency component higher than pi over 2. Let me say that again. In general, we should expect aliasing, but unless we're so fortunate, we're so lucky that our original spectrum does not have anything beyond pi over 2. In that case, if our original spectrum does not have anything higher than pi over 2, then we are fine. But mostly we are not so lucky, right? We can never guarantee that, okay, here is your, you can never guarantee that any signal would have no component beyond some kind of frequency. Okay, you have no control. So therefore, when we have no control, let's get the control. That's exactly what is meant here, right? You cannot guarantee that your input signal has nothing beyond pi over 2, but what should we do? Sorry, we should just get rid of anything beyond pi over 2 first, before we do the downsampling. Okay, that's kind of philosophy. So that's why we need a low-pass filter. We want to ensure that we don't have aliasing. So there's a sacrifice. In case our original signal might have something between pi over 2 and pi. Okay, there might be something for sure, but we're sorry. We need to get rid of them before performing downsampling. Otherwise, we see artifacts like that. Otherwise, we see artifacts like that in the image domain. Also similarly in the time domain. Okay? Some high frequency component might appear at low frequency, and that's really bad. You can argue that's worse than just get rid of all the high frequency to begin with. Okay? You can argue for that. Okay? All right, any question here regarding downsampling? So now we have upsampling, downsampling. It so happens that when we perform upsampling, we perform expansion first, then low-pass filtering. But for downsampling, let's remember that we need to perform low-pass filtering first. And then we do whatever we need to do to remove, in this case, to remove every other sample. Or to just preserve one sample in every 3 samples. That's downsampling by 3. Okay, that's what has been done in resizing the image or in resampling the time domain signal. Okay, any question here? If no question, let me ask you a question before we take a break, okay? What if we want to perform a change of sampling rate by a factor of 3 divided by 2, by a factor of 1.5? What if we want to increase our sampling rate by 50%? So that means what if we want to change our sampling frequency by 3/2? That is to say, from sampling rate fs to 1.5 times fs. Any suggestion? What if we now have the desired ratio of sampling rate conversion is not an integer? What if it is a fractional number? A simple fractional number, let's say 3 divided by 2. A factor of 1.5. What should we do? Any suggestion? You finished lunch, right? Why don't you say something? You took a look at me. Okay. 这位同学，这边几个都看一样。In Chinese is okay now. What should you do? Any suggestion? First up, then down. Okay, why? Why not first down, then up? It's equivalent, right? So we only need to use low-pass filter one time. Why is that cool? 直觉 intuition. Can anybody say, do you agree with his intuition? First up, then down. Does anybody agree with that? Yes, you agree. Why?
I think I agree because if we make first up, we are not deleting information in the first place.
Okay, I like your answer. Yeah. So, does everybody see that? Hear him? Okay, the question is, if we perform downsampling first, then upsampling, of course, the end is a signal with exactly that sampling frequency, for sure. You can always do that. But if we perform upsampling first, the advantage is that we are not removing any information. Right? Because we say when we downsampling by 2, we need to avoid aliasing by first applying that low pass filter. And that's potentially that could remove information, remove anything that is from pi over 2 to pi. Okay, so all the high frequency components are removed. Then we perform upsampling, okay, so the information is lost. Okay, so I think I would agree with both of you, the intuition from both of you. Okay, first up, then down. But what is the potential disadvantage? Maybe you need more memory. That's all. Right? First up, then down. As long as you have enough memory, please first up, then down. Okay, so let's take a break for 10 minutes. Let's get back here, continue. And I want to switch to PowerPoint.